Good evening, everyone, and thank you for the invitation, Chris, and it's my pleasure to speak to the pig people. I usually speak to the beef people, and so I had to redo my slides in order to make sure I was getting to the right audience, and I think that's something that as science communicators we need to think about a lot when we're giving a talk, to make sure that we're hitting the right crowd. And so a lot of what I work on is science communication and the importance of visuals in our media, and I think I'm a bit of a fan of films and videos, as you will soon see, because a lot of this presentation actually involves not me talking, but rather me showing. And if a picture shows 1,000 words, then a movie shows a lot of words, and I'll talk about that a little bit. So I would like to talk a little bit tonight about, can biotechnology bring home the bacon? And I think it's always nice to set the context of where we are in terms of our food production, and the fact that, in actual fact, it's a little known fact that fish, when you combine both cultured and wild together, are our #1 animal protein source, followed closely by our friends the pigs. And chickens are gaining on you, but at the moment that's the second most. It's the most important terrestrial land source, and not news to this group. And I must admit, in doing research for this talk, I'm pretty impressed with the prolificacy of pigs. I have a new appreciation for them. Working in beef cattle makes us look pretty bad, to be honest. But anyway, that's fine. But I think that the reason that this is so important is given the projected increase in animal protein over the next 20 or so years. And so I think this graph is maybe of no surprise to anyone in this audience, but maybe is to a more urban audience, in terms of the increased demand for animal protein, mostly due to the dashed lines there associated with the developing world, where you can see milk and meat increasing, and most of that meat increase is going to be in the developed world, and it's going to be fulfilled by two species, the terrestrial pigs and chickens. And so as a geneticist, if I wanted to select for a more efficient pig, what would I look to do? Well, the amazing thing about pigs, of course, is their litter-bearing potential, and so I would probably do something like select for increased litter size. I might do something like increase the number of litters that were born per year. I might increase the amount of lean meat per animal that's born, pork or bacon, if you will. Decrease the amount of time needed to get to market weight would be another logical selection objective. Maybe improve the efficiency of feed conversion, or the feed conversion ratio. And maybe, none of this is particularly new to this audience, decrease the amount of feed needed to produce a finished pig. Well, shockingly, that's exactly what pig breeders have been selecting for. And if we look at US domestic pig production per sow from 1930s through to 2015, it's actually pretty amazing, the productivity of the current sow, and this is 2015 numbers, I'm sure we've improved since then. 4,200 pounds of finished pig per female. Kind of puts beef cattle to shame. We're lucky if we get 700. And so I think that's a really amazing number. And often when talking about this type of genetic improvement, which is rarely thought of as a component of sustainability, I like to have a look at, well, what would it look like 35 years ago when we were raising pigs versus today? And this is only in the last 35 years. If you compare, the feed conversion ratio has gone down from 3.2 to 2.6. The lean meat per carcass has gone down. The pigs marketed per sow has gone up from 9.2 to 22, and I was speaking with two pig breeders yesterday in Canada who said 22, more like 29, and I'm like, okay, this is the average from a paper that I took, so even that I think is being stripped out. And pork produced per sow per year, 4,200, up from 1,770. So the number born per year, or weaned and marketed per year, I think is the number that really caught my attention, because I always like to do the scenario of, okay, let's not genetically improve our pigs. Let's preclude access to innovation in our breeding programs. Let's stay with the good old days. What might that look like? And if not for pig genetic improvement in the last 35 years, what would happen? Well, market pigs would today require 4% less feed than they did 35 years ago, and they produce 17% heavier carcasses. Of the 41-pound increase in live weight, 93% of that increase is lean muscle, i.e. meat, provided on each carcass. That's allowed for a 28% increase in pork production, with only a 10% increase in the annual number of animals harvested over the same time period. And if you add all that together, the average US pig farm is producing 4,200 pounds of live weight per sow per year, compared with 1,770 in 1980. And if you do the math and say, let's stop back in 1980, maybe those were the good old days, maybe with this audience the 60s were the good old days and we could make it look even better, without these genetic improvements, it would take another 9 million sows, in addition to the 6 million that we currently raise, to produce the same amount of pork that we produced in 2015 using 1980 figures. And 1980 is not that long ago, 35 years ago. And so that's what we've done using conventional breeding. And for the most part, there hasn't been a lot of public opposition to conventional breeding. And I'm glad that we've been able to use conventional breeding, because otherwise the environmental footprint of our food production will be dramatically higher. But there are some other things that I would like to do if I was to select for a more efficient pig. Ideally, I would like that pig to more efficiently digest the feed that goes into its stomach, so it has less pollution coming out the back end of the pig. Or maybe I might like to improve the health profile of the products that come out of a pig, heart-healthy bacon, if you will. And these might sound like hypothetical concepts, but they're not. They're actual applications that were developed using the process of genetic engineering. This very controversial topic, as it relates to plant improvement, has more or less been stopped in animal improvement, but that's not because scientists didn't have the vision to create these products. If we look here back in 2001, we see the infamous EnviroPig coming out of Guelph, public sector sponsored research that basically expresses phytase in its saliva and can more efficiently digest indigestible phytate into phytase, and basically reduces the phosphorus coming out the back end by about 75%. Currently shelved in the freezer at Guelph. Similarly, University of Missouri worked to insert a gene that enables the conversion of fatty acids to omega-3 fatty acids, effectively increasing the healthfulness profile of bacon. 2006, we see public sector money shelved. And part of this is due to the controversy associated with the use of genetic engineering. I think this little video that was created a few years ago nicely summarises the importance of genetically improvement in our animal production systems.
Once upon a time there was a milk barn where we used to milk a cow or two. Remember how we worked away the hours, dreaming of fun things we'd rather do. Those were long days, my friend, we thought they'd never end. We'd plow and toil forever and a day. It's not the life we choose, we work and never snooze, for we were poor and hungry every day. La 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 la, la 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 la, la 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 la, la 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 la. Then the hungry world came calling to us. We had to get productive right away. We could not sit by and watch them languish. Our science and genetics saved the day. Those were long days, my friend, we thought they'd never end. Plow and toil forever and a day. It's not the life we choose, we work and never snooze. Those were hard days, oh yes, those were hard days. La 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 before the pig barn, reflecting on the way things used to be. In the mud I saw a strange reflection. Was that hungry person really me? Those were long days, my friend. We thought they'd never end. We'd plow and toil forever and a day. We'd not the life we'd choose. We'd work and never snooze. Those were hard days. Oh yes, those were hard days. La 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 though some may yearn for simpler farmsteads, history shows this does not serve the poor. Technology has helped us feed more people, and now is not the time to shut that door. Those were long days, my friend. We thought they'd never end. We plow and toil forever and a day. It's not the life you choose. We work and never snooze. Those were hard days. Oh yes, those were hard days. La 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 la.
So if anyone is interested in that video, I often get asked where they can get to it. You can get to it on YouTube. It's called Were Those the Days, My Friend? And so it really, I think, does a job of explaining what's been going on in animal breeding. And I think that at the moment we're facing an interesting world of alternative reality as it faces agriculture, especially around the use of genetics in our production systems. And I want to take you through a little walk through a current Hollywood video or movie that's out there, funded by Netflix. Any of you heard of the movie Okja? Okay. This will be fun. All right, we got one hand went up. So that's what a pig looks like. I don't know if you guys have ever seen a pig before, but that's what a pig looks like. I'd like you to notice its snout. I'd like you to notice its beady little eyes and its somewhat humanistic expression, which makes it very easy, I think, to anthropomorphize things as it relates to pigs. They are very intelligent animals. And I'm going to tell you a story about what I used to think was a movie distribution company called Netflix. However, I've come to realize that actually Netflix isn't a movie distribution company. It's an organization with an agenda around agriculture. I thought they showed movies, and I thought they showed all movies, because God knows I've watched a fair range of them myself on Netflix. But they recently invested $60 million in the production of this particular movie called Okja. So let me set the context here. Okja is a pig that gets to market weight in about 10 years of age. So is that about where you guys are right now? I'm not sure that I know the industry very well. And it was developed by an evil company that starts with M. I think it's something like Mon, but not Santo. It's something different to that. And they have genetically engineered these pigs to be more efficient and to produce less waste and to feed more people. Things that resonate very closely with me, because actually that is why I'm interested in animal breeding. I do think that genetics has a huge role to play in sustainability, but they're doing this with an evil attempt to make more money and to hide GMOs and get that out into the food supply without admitting that they're GMOs. And so in some random location, they've created these pigs that are more efficient, that they've then distributed to throughout the world to 10 different locations to be raised by rural farm families. And this one particular pig was raised in Korea. Its name's Okja. And after 10 years, the evil company comes back to reclaim the pig because they think it's a particularly superior pig, and they want to basically breed with it and make more of these pigs. And they steal it from the little girl who's been raising this pig for the last 10 years. Needless to say, things don't go well. Science is reflected very negatively. Scientists are evil and doing this all for corporate greed. And I think what concerned me most, and maybe I need to get over this, is the biology of the creature they created to be this genetically superior pig. It doesn't have a snout. And the most surprising thing to me in all of it was they took away the fact that it's a litter-bearing animal with 7 teats on each side, or maybe even 8 teats on each side, and created a creature that has some sort of a goat udder on a pig. And I'm not sure how that can exactly fit with improved efficiency. But I want to play you a little clip, actually the trailer of this movie, which is science fiction. It's not meant to be a documentary, although God knows Netflix has plenty of other documentaries that are equally science fiction that are called documentaries, like Food Inc. But I want to now give you a little feel for how this documentary goes. If you haven't seen it, and you have Netflix, I would encourage you to watch it, because I cannot tell you how many people, when I talk about genetic engineering in animals, say, but nature finds a way. And where did they get that line from? Jurassic Park. And so if you don't think this is where we're going with animal breeding, then you don't hang out in California as much as I do. And that's where things start. And I haven't heard much response from industry. I think I saw, I think one person maybe put up their hand that they'd seen this movie. My kids have seen this movie because they're at college, and that's what kids watch, Netflix. And I think it's important to make the defense of the importance of breeding in our sustainability of our food production systems, and we haven't done a good job of that. Because what is it that makes a pig a pig? It has a snout. It has beady eyes. It's litter-bearing. It's a single-stomached animal. It has cloven hooves, not what that pig has, and it has a curly tail. $60 million budget this movie had, and it has been seen by many, many people. You may know I was also involved recently in a movie called Food Evolution that's about the science of food production and specifically focuses on the topic of GMOs. How many people in the audience have seen Food Evolution? Okay. Better than one, that's a good thing. It was funded by the Institute of Food Technologists, who are a scientific society of food technologists that take food from the farm gate through to the consumer. And they funded this movie because they were tired of false information around food technology, specifically things like meat irradiation and process, the requirement for additives and having chemicals in our food. They didn't really necessarily want it to be specifically about about GMOs, which is more of a production issue than a food technology issue. But that's what the producers decided to make it about, because this is such a political and controversial issue. This movie, which I'll play you the trailer of in a minute, was produced by a Hollywood, he's an Oscar-nominated director who approached Netflix to see if he would play this hour-and-a-half fact-based video narrated by Neil deGrasse Tyson, a well-known science communicator. And Netflix said no, they didn't think their audience would be interested in that movie. And so it is now available on Hulu, but I'll give you a 4-minute trailer of Food Evolution, and I would encourage you that haven't seen it yet to have a look at this movie.
The survival of our species has always depended on advances in agriculture.
Climate change is going to scramble this "how are we going to feed the world" debate.
This is all about companies.
This is about money. This is about power.
It's much easier to sell fear than it is science.
If you don't have food, then you're going to steal, you're going to kill someone.
So, how do we make the most informed decisions about how we feed ourselves?
Hell no! GMO! Hell no!
The three most terrifying letters in the English language are GMO.
I wondered how many people really know what they are.
I don't know.
I know it's bad.
Genetic engineering is a modern form of breeding.
The goal is to add useful traits into food.
I am concerned about some of the health issues related to GMOs.
More colds, autism, susceptibility to hepatitis, cancer, HIV.
There's absolutely no proof to a health hazard.
Never trust one opinion. You look at the consensus of experts.
I don't think that genetically modified organisms are dangerous.
You're either going to be GMO or you're going to be organic. They cannot coexist.
If this is an organic planet we're going towards, you would see all the rainforest destroyed just to feed the current population.
This is something I'm going to look into.
Some people can say wild and crazy things.
I trust the social media more than most medical doctors, more than the CDC, more than the FDA, more than the EPA. I don't need a scientific study.
Things like that.
We humans are wired to make our minds up and that's it.
We make decisions based on our gut. When was the last time you changed your mind?
Our intentions were honorable. We were trying to protect the future of the planet and the health of our children. It begs the question, how do you know that GMOs are the enemy? What if we got it wrong?
The good thing about science is that it's true whether or not you believe in it. You see, that's the...
So if anyone's interested, as I mentioned, it's available for free on Hulu. If you're over 40, you may not know what Hulu is. You can ask your kids. Otherwise, you can rent it from Amazon, iTunes, Google Play, and YouTube. And I would encourage any of you that teach to use it in your curriculum. So back to the topic at task, which is the use of biotechnology and whether it can bring home the bacon. And I want to talk about the regulatory process associated with genetically engineered animals. And so those of you that haven't paid attention because it really hasn't entered your radar, to get a genetically engineered animal onto the market, you have to go through a mandatory pre-market regulation of review of genetically engineered animals, and that's done by the FDA. And basically, genetically engineered animals have historically, in the last 20 years, been regulated by the Food and Drug Administration as a new animal drug. And that's because the new animal drug regulation defines a drug as something that alters the form or function of an animal. And in this regard, the introduced recombinant DNA, the rDNA, that alters the form or function of the animal, in the case of the fish, for example, that grew faster, was considered to be the drug. And the animals that are modified by the recombinant DNA techniques are drugs, but it's not actually the recombinant DNA that's thought to be the drug. It's not actually the animal that's the drug, it's the recombinant DNA in the animal that's the drug that produces the protein that makes the animal grow faster. And so in that regard, it gets regulated much like a dog wormer would get regulated if you were trying to bring that to market. You have to show basically that it's safe and effective at whatever it's meant to be doing as a drug, and that it's safe for the animals, safe for the environment, safe for the humans that are consuming that product. And you have to go through this hierarchical risk-based evaluation starting at the bottom, where you have to say what it is you're doing, what gene you're introducing into the animal, where did it get introduced, how many copy numbers were there, when is it expressed, is it inherited faithfully from generation to generation, is it safe, in other words, is a protein itself an allergen or a toxin, is it safe to the animal, does the animal abnormal or have unexpected phenotypes in any way, does it work, does the animal grow faster or do whatever it's meant to do, and then you'll get a regulatory decision, and then there's post-market approval, just like a dog wormer, basically. And so let's have a look how that went for the only animal that's ever been approved for the commercial consumption for consumption in the United States, and that's the fast-growing salmon. This is a salmon that was introduced was developed by public sector researchers in Canada, and the actual founder event of this fish, where they injected the recombinant DNA containing a gene from Pacific salmon into the Atlantic salmon happened back in 1989. And basically it was injected to produce animals where we've got full sibs shown here in this image, one of which is carrying the transgene and one of which isn't. I'll let you decide which of those is. It doesn't get to market weight, or it doesn't get to twice as big at the end of its life. It gets to market weight in half the time. So it doesn't grow to be a monster salmon, it just more rapidly approaches market weight. Have you guys ever selected for pigs that do that? Just curious. Oh yeah? Actually, it's a selection objective. I thought it might be. 1989 was when this initial founder event happened. Do you remember the 80s? It was a long, long time ago. That was back in my bull riding days, and probably my hair looked a little bit like that too. But have a look at that quote-unquote mobile phone. What if in 1989 we had said, you know, we're not sure of the long-term effects of mobile phones. We need to do a 25-year long-term safety evaluation before we enable this technology to develop any further. None of you would have iPhones in your pocket right now. We'd be sitting back waiting for that to happen. And then we look at the timeline of the approval of the AquaAdvantage Salmon. It's basically more than a quarter of a century to get a fast-growing fish to market. And it hasn't even got to market, because as I go through this sad little story, you'll see it was founder fish was produced in '89. Then the FDA received the first attempt to bring it to market back in 1995. The first regulatory study started in 2001, and they finished all their regulatory studies in 2009, showing that the fish grew faster and that the product was safe and safe for the environment because they were going to grow it in contained land-based conditions in the highlands of Panama. And then in 2010, they had a veterinary medicine advisory committee meeting where a group of independent veterinarians and actually some subject matter experts, including myself, looked at all of the data and saw if there's anything the FDA missed, because the FDA scientists have spent 8 years evaluating all this data. I thought that was unlikely, and we didn't. We said, yeah, it looks like it's a fast-growing salmon. That was pretty much what the data showed. And then there was 5 years of radio silence from the FDA, where it was neither approved or disapproved, nothing, just nothing. And as a company trying to bring a product to market, if that was a dog wormer and it was Pfizer or whoever, Merck, that's just really difficult to deal with from an uncertainty perspective. Finally, late in 2015, it was approved, and they estimated by that time it had cost about $70 million to bring that product through regulatory. And you might think, well, that's good, it had a happy ending, but no, it's still not allowed to be sold in the United States. And the reason for that is that in January 2016, there was a group of senators from the great state of Alaska. Anyone know anything about salmon in Alaska? Does that ring any bells? So a competing business interest state brought in legislation that precluded the sale of this product in the United States until such time as labelling had been derived for it and additional studies had been done on this fish. It's already had a quarter of a century of studies, but the concern is about interbreeding with the Pacific salmon in Canada. These are Atlantic salmon that are female, triploid, getting raised in the highlands of Panama. And by the way, Atlantic salmon and Pacific salmon are like dogs and cats. They're different genuses, and they cannot interbreed. And so this is effectively just political interference in what should be a science-based process. Subsequent to that, a group of environmental groups sued the FDA for approving the salmon. Interestingly, our friends to the north in Canada, who have a product-based regulatory system that looks at the risks of the product, approved it, and it can now be purchased in Canada and has been sold up there for human consumption. And then finally, to add a little salt to that wound, the FDA billed AquaBounty, the company trying to commercialise the fish, $113,000 new animal drug user fee application for their approved salmon, which they're not allowed to sell in the United States. And so, needless to say, I'm not very excited about ever developing a genetically engineered animal, and I doubt as a public sector scientist working at a university I ever could bring a product through regulatory. So now let's talk about genome editing and whether it will or will not be regulated as a genetically engineered organism. So I'm not going to go into the specifics of genome editing because that would be scientific and kind of boring. And really the point is genome editing is a way to cut DNA at a particular place with a pair of scissors. And the scissors can have different colour handles, whether they're talons or CRISPRs or zinc finger nucleases. You can do a direct cut, which can mutate a gene, if you go down the left-hand side of that graph. And that's very analogous to the double-stranded breaks that happen whenever we're exposed to sunlight or, God forbid, alcohol. That's basically the basis of evolution, and that is where we get our variation that we make our traditional breeding selection decisions on, and the reason that you and I don't look exactly the same. If we go down the left-hand side of that image, you can introduce DNA, and that DNA may be sequences that are coming from maybe a different breed within the species you're working on. Maybe you're bringing in something from an Angus into Holstein, or it could be DNA from a different genre or even kingdom. And that way it's very analogous to recombinant DNA or transgenesis. So depending what you do, there's different approaches there. And so how can this be used in animal breeding? Well, I'm going to give you an example from my lab where we're collaborating on a USDA grant with a company called Recombinetics, where we've basically introduced the allele from Angus that don't grow horns into dairy cows, in this case Holsteins, that do grow horns. And what that does, because it's a dominant trait, is stops those cows growing horns genetically. The following image or video, you might have seen, I'm quite keen on videos, explains to the public what it is we're doing and why it is we're doing it. And I think from scientific communication perspective, we spend too much time explaining how and not enough time explaining why. So for you pig people, if you've never seen a dehorning, you're about to see one.
If you look at our dairy cows and our beef cows, there's a lot of differences between them. So dairy cows have been bred to be very optimal for dairy production. And as it happens, that brought along the horned phenotype. In other words, dairy cows grow horns. If we look at our beef animals, they've been bred for optimal beef production. And as it happens, Angus, for example, is a breed that doesn't have horns. And we don't really want horns in dairy production systems because the animals hurt each other with the horns and they can hurt the human workers.
It's a widely accepted husbandry practice that we dehorn cattle, both for the safety of the cattle as well as for the safety of the people that take care of the cattle and work with them. The way that this budding procedure is done here routinely is we will administer a lidocaine block. A lidocaine is a local anesthetic similar to what you might get at the dentist's office for a procedure that might be painful. And then we use an electric dehorning or disbudding instrument that provides heat around the horn bud to kill the cells that would grow the horn. The consumers are concerned about the way we care for our dairy animals, and they expect us to do a good job of providing care and being concerned about animal pain when we have to perform procedures. So I think it's important that we keep those factors in mind and do the best job that we can to try to minimize pain and discomfort.
We're working in collaboration with a company called Recombinetics, who had a vision to try to use precision breeding or genome editing to introduce genetics from Angus cattle to the Holstein dairy breed to produce dairy cattle that don't grow horns. And so we haven't altered anything about all of the genetics that makes them great milk producers and you know, all of their Holstein genetics is still in place. What we've basically done is a very precision technique of just introducing one trait that we want, which is polled or hornless, and we haven't altered the rest of the genetics.
With the change in technology, it looks like that we can achieve the goal of having calves born without horns and not have to give up the genetic capability of those animals. So it looks like a win-win situation. We've still got very productive, efficient dairy animals, And we now have the opportunity or possibility of no longer needing to dehorn or disbud dairy calves.
So because this is a little bit of a scientific audience, I will give you a little bit of the how. And basically what we did here is, in the case of Holsteins, they have at their polled allele, the allele that grows, or the gene that grows horns, a 10 base pair segment in yellow here that was replaced by that 212 base pair sequence that's in the Angus genome. And the sequence then that is in the resulting animal is sequence that exists already in cattle. It's basically the Angus sequence now in Holsteins, but nothing else about the genome has changed. This was done using talons to introgress that DNA, and then those animals were actually cloned using somatic cell nuclear transfer cloning, and 2 bull calves were born in 2015, April. Those of you that know the lifespan of a bull calf on a dairy won't be surprised to see that this is what Spotty Guy looks like now, and this is what happened to Burry. So we collected semen from them and inseminated horned Hereford cows at UC Davis, and just actually September, we had 6 animals born, 6 offspring of these bulls born, and they inherited the dominant polled phenotype or allele from their dad, and so far have a polled phenotype, and the horned Hereford calves that were born alongside as controls have all started to have their horn buds emerge. So we're confident that Mendel actually did know what he was talking about, and so we're pretty happy that we've confirmed Mendel knew what he was talking about. So the question is, will breeders be able to use gene editing, or will it go the way of GMOs? And what do I mean by the way of GMOs? Well, anyone that's been around the last 20 years will know what I mean. We basically cannot use that technology in animal breeding. We were aware of this fact back in 2011 after the Transgenic Animal Research Conference, which is a conference that's organised by UC Davis every second year and has been going on for about 20 years now, so we just had our 10th conference. But back in 2011, we started to get a whole bunch of abstracts and papers on the utilisation at that time of talons to introduce double-stranded breaks and do interesting genetic alterations in animals in the research lab. And it became pretty clear that we were going to start having these products coming through the research pipeline, and it was really unclear at the time what the regulatory would be around a product where maybe you went in with your pair of scissors and all it resulted in was a mutation, like a base pair got dropped, which threw your protein out of frame, so you no longer produced a functional protein, so you created a knockout effectively. And so at the time we wrote a letter to the FDA, myself, my department head Jim Murray, and a faculty colleague, Elizabeth Marga, asking for clarity on the regulatory understanding of that. And so back then, that was September 2011, and we got a mail right back from the FDA in 2011, and I've kind of highlighted down there that they're aware of the fact that these techniques are coming along, and they had scientists at the conference. And they're going to work to develop a regulatory framework, and we hope that we can call on you from time to time to gain a greater understanding of these important emerging technologies. Well, still waiting for that call. So that was 6 years ago, and then in January of 18th, out of the blue, to some extent, came this draft regulatory guidance 2 days before the current administration took office, which basically considers all gene-edited animals whose genomes have been altered intentionally to be drugs. Think about that, breeders. Have you ever intentionally altered the genomes of what you're breeding for? So in the past, the FDA has used the term genetically engineered to refer to animals containing recombinant DNA. In other words, in the case of the salmon, the recombinant DNA that came from the Pacific salmon expressed in the Atlantic salmon. And that was altering the form or function of the animal. The new guidance removes that language and just uses the term animals whose genomes have been altered intentionally. That removes the RNA trigger for regulation and puts the intentional alteration in its place. And the presence of any intentionally altered genomic DNA produced using modern molecular technologies in an animal is going to trigger mandatory pre-market animal drug evaluation, irrespective of whether the product if the product is novel, the DNA is novel, or the novelty of that alteration. And the guidance includes nucleotide insertions, substitutions, and deletions. So the absence of a SNP is now a drug. I'm not sure how you track the absence of a SNP, but I think that it clarifies that selective breeding and random mutagenesis followed by phenotypic selection is not included. And so if there's a random mutation that knocks out a SNP that was done by nature, that's not going to be regulated. But if I make the same random mutation in an animal, for example, myostatin, that will be regulated because I intended it rather than nature randomly doing it. Okay. And in general, each specific genomic alteration is considered to be a separate new animal drug application. So if I knock out a SNP on chromosome 2 and a SNP on chromosome 3, that's two separate new animal drug applications that I have to go through. Any of you that have sequenced a few animals will begin to realize how ludicrous this proposed regulation is. Because are these guys a drug? The naturally occurring bovine allele at the polled loci, what is the new animal drug in this case? I argue this guy is a polled Holstein. He's not a drug. And we have actually sequenced these animals, or Recombinetics did, to 20x. And the only difference between these animals is that 202 base pairs that's inserted at the polled loci. And it really, I think, is not that this guy is a drug. And the problem is that breeders won't use the existing polled Holsteins or introgress the polled loci from Angus, which could be done biologically, just because of how much that would slow down the rate of genetic progress. And we spoke today about the importance of delta G. And if we look, we haven't introduced this trait into our existing elite Holstein genetics because we don't want to lose all of that progress that we've made in our milk production and all of the other traits that make dairy producers great cows. And so the phenotype is no different whether it comes in from an Angus or is introduced through editing. They both are going to be polled. They both are going to have animal welfare benefits from that. There's no food safety concerns associated with polled, or else we wouldn't eat Angus burgers. It's going to take many generations to introduce it through introgression, but it'll take one in the case of editing, and there'll be no linkage drag associated with it. And it's just not going to be feasible if this is going to be regulated as a new animal drug. And does it really, from a scientific perspective, make sense to regulate polled dairy cattle differently to polled Herefords? I don't think that's a very justifiable position. And if you look more generally at the data, which is what science-based regulation is meant to do, in one recent analysis of whole genome sequence data from 234 taurine cattle, there's about 28 million genetic variants between different bulls of the bovine breed. And if we look at a recent paper from Michelle Georges, every new animal is expected to have around about 65 de novo mutations due to spontaneous mutagenesis that happens from generation to generation, of which approximately 5 will be small indels and the rest will be SNPs. How are we going to differentiate those from those associated with genome editing, unintended effects of genome editing? It becomes impossible, given the plasticity of the genome, to say what's done by us and what's done by nature if we're going to have that type of a regulatory. And basically, the draft regulations that consider all animals whose genomes have been altered intentionally as drugs is really saying this is more of an arbitrary distinction based on ideology than science, because we all contain DNA variations. The fact we have DNA is what makes us grow how we grow and alters the form or function of this animal and all you animals in here as well. And so when we start saying that naturally occurring variation is a drug, we go into crazy land. And really, making it about whether people will be involved rather than the safety of the end product is not how we have a science-based regulatory system. That's an ideological-based regulatory system. It may as well be the European precautionary principle, because this approach is going to preclude access, certainly from all the public sector breeders that are around the tables here, and certainly from small companies, and might even stop big companies, because you're going to have to basically edit all of your elite pig lines in your industry. And if you have to go through a separate new animal drug application for every line that you're editing, it's just going to make it impossible possible. And so you might think, well, this isn't my problem. You know, the pig industry, you've told me about polled, but that's not us. It actually is your problem, and it's your problem. And I think that for too long, scientists have sat back and looked at the process-based regulatory framework that has basically been operating around the world for recombinant DNA organisms and haven't said, the emperor has no clothes on here. There are no unique risks associated with this breeding method. We should be focused on the risk attributes of the product, not the breeding method that was used to introduce those modifications. And in the case of plants, we're using mutation breeding, which is wildly less predictable than these precise methods that we're using here. And yet we have no regulation around that, and we've had no safety concerns associated with that. And I really encourage you to be concerned about this as scientists if you want your industry to have access to this innovation. And I'll finish up with a couple of applications in your industry, and that is, if I also could do these things in selection, I'd also like to select for pigs that didn't get sick, the holy grail, disease-resistant pigs, and also maybe reduce the amount of fat and improve piglet survival. And I'm going to go through some papers that have come out in the last couple of years that use this technology of genome editing. One that's probably familiar to you all, and I think is a nice complement between what I've been talking about with breeding and the PRRS symposium and you coming together for this keynote session, disease-resistant pigs for PRRS, basically using editing to remove the protein that is the target entry point for the PRRS virus. This has been done by researchers at the University of Missouri. There's groups at the Roslin Institute that have been working on the development of disease-resistant pigs to the African swine flu, and that's basically, it's African swine fever. And basically what they're doing there is an introgression of an allele from the African warthog that they think will give that pig immunity to African swine flu. Now, they have to do the data and research to determine whether that's true or not, but they have actually reported this ability to do mammalian interspecies substitution of an immune modulatory allele by genome editing. Most recently, Roslin also has developed PRRS-resistant pigs using a slightly different approach of just knocking out a particular intron in the protein that's the attack point. And then recently, China came out with a piece where they've used genome editing to produce pigs that have low fat and increased pig survivability. And I think that we may not end up using it in the United States and the worried West and the wealthy, but I do think that this technology will get used in other countries. And I think it's up to us to call out policy that's not based on science, or else risk losing access to innovation in agricultural breeding programs. The draft guidance that I mentioned that the FDA put out has not become law. It's still draft, and they had a public comment period which is now closed. But there is a letter that's gone from several congressional members to the FDA asking them to please reconcile and make the regulations around genome-edited plants and animals the same. And the USDA and the plant approach is if you're not introducing novel DNA, then that's not going to be considered to be a recombinant DNA organism or a new animal drug in the parlance of the FDA. And really, if we don't get that right, then I think we should probably stop doing research with this technology because we're not going to be able to use it as a translational tool. Maybe we can get some basic research discoveries, but we won't be able to use it in our animal breeding programs. And so, to me, regulatory processes should be proportional to the risk and consistent across products that have the same level of risk. And currently, if something's produced by nature, it's okay, and given a free rein, and if it's produced intentionally by breeders, then it has to go through this regulatory process, and that really doesn't make very much sense. And to date, the GE regulatory burdens have been way out of line with the risk posed by the products and have more or less precluded the use of this technology in any sense in animal breeding programs. Current regulatory language should be science-based. Human intention is not associated with risk. It's not the predicator of risk, and the regulation of every drug, every SNP as a drug, is just nonsense. That's just it ignores basic biology. And given the importance of enabling safe innovation in breeding, there's an urgent need to get regulatory harmony around this within the country and more generally globally, because basically we're going to lose access to the technology. And so I think that's a really important message around this particular topic. But I would like to finish on a positive note, as Food Evolution does, I think, because I do think this is an area that has a lot of potential, and there's nothing that's more positive than graduate students. And so I'm going to play for you a little video that a group of my graduate students put together to say what they think of the potential of this technology. And in keeping with my lab, it's set to music, and it's going to be They Can't Stop the Feeding.
I got this laser inside my scope. I see them cells to edit when I turn it on. All through our research, we make our cuts. We're editing genes to limit what we might achieve. I got that bike bed in my pocket, got those lab shoes on my feet. Feel that thrill of innovation every time. Ooh, I can't take my lens up off it. Yeah, even high fidelity. You're gonna like the way we use it, so don't stop it. Without the research, everyone knows no way to feed when the populace grows. When we edit, well, it already shows. So just imagine, just imagine, just imagine. We can't do when we advance. Right now I might change the world, just advance. All the things I could do to those advance. And ain't nobody stopping soon, so keep advancing. I can't stop the feeling. Just advance. Stop the feeling. Just advance. Ooh, it's nothing magical. There is a method and a reason it's feasible. I need a theory and two controls to test my idea, no bias, edit that genome. I got that bike bed in my pocket, got those lab shoes on my feet. Feel that thrill of innovation every time. Ooh, improve global problems with that sustainability. You gotta like the way we solve it, so don't stop it. Without the research, everyone knows no way to feed when the populace grows. When we edit, well, it already shows. So just imagine, just imagine, just imagine. Advance. Right now I might change the world, just advance. All the things I could do to those advance. And ain't nobody stopping soon, so keep advancing. I can't stop the feeling. Just advance. Stop the feeling. Just advance. Stop the feeling. Just advance. Stop the feeling. Keep advancing.
Brink, can you stop?
You notice we threw some pigs in there right at the end for you guys. So thank you very much.